Now we're moving on to chapter 18, which is on thermodynamics. So where thermochemistry in chapter 9 was all about enthalpy, basically, and heat and work and energy, this ties that together and kind of takes it a step further. So thermodynamics predicts whether a process is going to happen spontaneously or not. And if a process is non-spontaneous, it can still happen. It just means that it's going to require you to put in energy for it to proceed forward. So is it going to happen or not on its own? Well, we're going to need to compare the chemical potential energy of the reactants to those of the products. And for the free energy. And so if the system after your reaction happens has less potential energy, so is lower than the system before the reaction, is thermodynamically favorable. So if we think about this as potential energy of reactants versus products, your products will be lower in chemical potential energy. Spontaneity has nothing to do with how fast or slow a reaction happens, just whether it's going to happen on its own. So you can have spontaneous reactions that go very, very slow. So for example, diamond converting into graphite, that happens. It just happens really, really slow. If a process happens spontaneously, then it is irreversible. So you're not going to be able to get it to go backwards without putting in any energy. So for example, iron rusting, so that's happened spontaneously. If I want to get rust back into iron, that's non-spontaneous. So it's only going to go in one direction. A reversible process can go back and forth. This means that it is in equilibrium. So the net free energy equilibrium, so the net energy is zero. So we're end at the same chemical potential energy as we begin in. So if a process is spontaneous in one direction, by default it is non-spontaneous going backwards, or else it wouldn't have happened in the first place. So as we've talked about already, reactions can be either exothermic or endothermic. So spontaneous processes can happen when they release energy from the system. So exothermic processes are what most spontaneous processes are consisting of, because our system starts at a higher enthalpy and it ends at a lower enthalpy. Where endothermic is the opposite, where we're ending at a higher. And some spontaneous processes can proceed this way, so we're starting enthalpy here and ending enthalpy here for products. But what's going to influence whether a reaction can happen, an endothermic reaction can happen spontaneously, is the entropy. So, two factors affect the spontaneity of a reaction. That is the change in enthalpy, delta H, which we've learned all about in the past chapter. And it's the difference between the internal energies and pressure, volume, work. And remember, when we're at constant pressure, then enthalpy equals Q, blah, 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 all the stuff we've done. So, enthalpy, we are very familiar with this. The next one is change in entropy, which is delta S. And that is a measurement of the randomness of the system. So, are my products more random or less random than they started out with as reactants? So these are both factors. So now let's talk a little bit more about enthalpy, and then we'll talk about entropy. So with enthalpy change, we're going to have an exothermic process if our products have stronger bonds than the reactants did. So that means they are ending with more stable molecules. So something like this, right? So our products here are more stable. They have a lower energy, stronger bonds than our reactants did. Because energy is released, then enthalpy is a negative value, which we've talked about. When we have an endothermic process, then we have products that are weaker than the reactants. So we're going like this. So the products end up being weaker. Delta H, which is the difference between the reactants and the products, is a positive number, and energy had to get absorbed for that reaction to proceed. Delta H is favorable when exothermic reactions because we're ending at a more stable configuration. And so endothermic reactions tend to be more unfavorable, but they can still happen. Entropy, which is a new term for us, is another thermodynamic function that has to do with how ordered a system is. One of the more kind of fundamental definitions of it is how many ways a system can be arranged. So how many ways can we arrange the components in the system? The units of entropy are joules per mole Kelvin. So Kelvin on bottom. And remember the units of enthalpy are kilojoules per mole. So when we are going to be converting between the two, or using them both in an equation, which hint we will later, we're going to want to make sure that we are being in consistent units. And then one of the basic definitions of entropy, just on its own, is entropy S is equal to K, the Boltzmann constant, which is this very, very small number in joules per Kelvin, times natural log of W, where W is the number of equivalent ways, W, a system can exist. So when we have random systems, they require less energy than ordered systems. So think about, this is kind of a really basic example. When you think about your room, when it is ordered and clean, you had to put a lot of energy to get it that way. And once you're changing your clothes, it's way easier. It takes a lot less energy to just put them on the ground than it would be to stand up, walk to your hamper, and put them in there. So random systems tend to require less energy than ordered systems. So the first law of thermodynamics is that energy is not created or destroyed, right? Delta E of the universe is 0. So it's only being transferred between the system and the surroundings. The second law of thermodynamics says that the total entropy of the universe must be positive for a process to be spontaneous. So meaning that the entropy of the universe is always increasing, because processes are going to be happening spontaneously in the whole universe. When we have a reversible process, the entropy of the universe is equal to 0. When we have irreversible or spontaneous processes, the entropy of the universe is greater than 0, so always a positive number when the process is happening spontaneously. When our entropy decreases, that means then the surroundings is going to increase by an even bigger amount for a process to be spontaneous. So let's look at this situation where I have 4 particles on the left side and 0 in the right. And I have the stop clock that is closed. Once I open it, the gas atoms are going to diffuse around and distribute themselves into a variety of arrangements. The first state is they could all be in A. They could stay there. It's possible that they could all be in there at any given point in time. There's state B, where they could be over on the right side. There's actually other states where we have 3 on one side and 1 on the other, right? And then we have state C, where they're equally distributed on either side. Now these particles are not numbered; they're identical, so we can't really differentiate between them. And energetically, they have the same equivalent states because they're in that same volume. So it doesn't, as far as potential energy is concerned, it doesn't matter where they are, but it's more likely that we're going to have them in state C, where they're evenly distributed at any given point of time. It's just going to be more likely for them to be 2 in each side. And so that has to do with entropy. As we increase the number of molecules, the number of ways that we can arrange the molecules in the flask is going to increase. And so that has to do with entropy. The increase in the number of ways that we can arrange things, the higher the entropy. So if we look at state A and state B, where all of them are in the left versus all of them are in the right. The macro state is where each of those particles are identical and we can't tell the difference between them. There's only one possible way for them to be in there. When we look at microstates, we are actually going to be kind of numbering those particles and kind of keeping track. Even though they're identical, we're keeping track of who goes where. So with our state C here, where we have 2 and 2, I could have molecule 1 and 2 on the left and 3 and 4 on the right. I could have 2 and 3 on the left and 1 and 4 on the right. So you can see that with this, there are 6 possible ways that we can arrange the particles to have the same overall state. So that's where I was mentioning before, it's more probable that we see arrangement C because there's just more opportunities or more likelihoods of having the molecules be in this state. So on the other side, we saw that state A and B only have one possible way to be arranged, where state C has 6 possible arrangements. So the microstate that has the highest energy or the highest number of ways also tends to have the highest dispersal of energy. So our state C will have has a higher energy or entropy, higher entropy than A or B. So just like we did with enthalpy, we're going to be calculating the change in entropy, final minus initial or reactants minus products. Entropy tends to be more favorable when we're increasing it. So when it goes from a low to a high state. Changes that are going to, or things that will influence the entropy are going to be the state that they're in. So things that have more random state, if we think about solids versus liquids versus gases, which are going to be more random? Well, solids tend to be the least because they're kind of in a fixed position. And so there's not a lot of movement. They are pretty rigid. There's just those vibrations. And then liquids, there's still movement around. Now they're able to flow. So they'll have the next highest entropy. And then gases, entropy of the gases will be highest. There's just more ways that they can move around or more degrees of freedom for the particles. And so they're going to have more ways that they can be arranged. So more macro states, i.e. higher entropy. Also, reactions that have more number of products than reactant molecules. So if I have A plus B goes to 3C, then I have 3 particles here and only 2 particles here. So that would be an increase in entropy. Also an increase in temperature, because when we increase temperature, we're increasing the kinetic energy of the molecules. They're able to move faster. And then the last one, which I guess is completely cut off here, sorry on your notes, is when we have solids dissociating into ions. So that makes sense because we're going to have these like solid lattice structures where they're really rigid and strong, and then they're able to break free and flow into aqueous solution. So, when we have gases are really high entropy, more number of particles in the products and the reactants, increase in temperature, and something that is dissolving. So let's look at these. We're going to predict the sign. Is the randomness or the movement able to go down or up? So if I go from a gas to a liquid, I'm going from moving a lot to being more condensed. So my change in entropy is negative. I am decreasing my entropy. Solid carbon dioxide subliming. So subliming is where you go from a solid to a gas. So that's going from something really rigid to something that moves around a lot. So delta S is positive. N2O gas going to 2N2 plus O2. So I have 2 molecules here and 1, 2, 3 here. So 2 going to 3, so delta S is going up. So positive. The boiling of water, so that's going from liquid to gas. So that would be positive. We are getting more random. And then a solid calcium oxide plus CO2 going to calcium carbonate. So I have 2 particles going to 1 and a gas going to a solid. So for multiple ways, we have delta S getting less random, more ordered, so it'll be negative. So the second law of thermodynamics is that the entropy of the universe is going to be increasing for a spontaneous process. But sometimes we actually have processes that are spontaneously happening, even though it's going from something that's from more random to less random. So condensation of water, that happens spontaneous, even though water vapor is more random than liquid water. There are cases where our delta S process might be unfavorable, but we are still able to have that process happen spontaneously. So that means we need to be given a large increase in entropy change from the surroundings, right? The surroundings, so if my system is not happening in a spontaneous way, then my delta S surroundings, because remember, delta S of my universe equals delta S of my system plus delta S of my surroundings. So if the process is spontaneous, then this is positive. Now, if this is negative, then this must be much, much more positive than this one to overcome it. So the entropy in this case is coming from heat released by the system. So our system is releasing heat in an exothermic process. So in a process that is exothermic, that means that when that process happened, heat was released. Well, that heat goes from the system to the surroundings, and therefore it increased the entropy of the surroundings by increasing the temperature. When we have an endothermic process, then heat is coming from the surroundings, so therefore the entropy of the surroundings is going to go down because the heat got removed, so the temperature is going to go down, so this entropy of the surrounding goes down. So temperature is actually related to the entropy when we have a process happening. So the amount of delta S surroundings, so change in entropy of surroundings, depends on your initial temperature. So T0 is at time 0. The higher the temperature, then the less the effect we have on the removal of heat. Because if I have a really high temperature, then I'm already really warm. So if I add a little heat, remove a little heat, it's not that big of a deal because my temperature is already so high. When my temperature is really low, then adding or taking away any heat has a really big influence on the reaction. So the entropy of our surroundings, which will help us to know if a reaction is going to happen kind of spontaneously or not when our process is happening, when our process is decreasing our entropy, is the heat is related to the heat that is gained or lost. So the heat of my surroundings is equal to negative heat of my system, right? So if my surroundings gained energy, well, it came from my system, so the sign. So basically, if I have, I'm going to give a weird example. If I have 4 cookies, I'm going to lose 4 cookies. If I give it to somebody else, then they're going to gain 4 cookies, right? So if the system lost energy, then the surroundings gained it. We also mentioned that it's proportional to the temperature. So at a constant pressure and temperature, the relationship of delta S surroundings is equal to the negative heat of my system divided by the temperature, which when we have a constant pressure, then remember my heat of my system is the enthalpy. So negative delta H of my system divided by my temperature. And that's in Kelvin. That's very important. Very, very important. Okay, Kelvin. So this is the reaction. That's the end result. So let's practice that. We have a reaction here of propane plus oxygen going to carbon dioxide and water. Enthalpy of the reaction is negative 2044 kilojoules. So calculate the entropy change in the surroundings associated with this reaction. So first of all, let's kind of think about our entropy. I guess I'm getting ahead of myself. So let's do B first. Determine the sign of entropy change for the system. So my system is, I have 6 gas molecules on my reactants and 7 on my product. So I know that my delta S of my system is going to be positive. I went from 6 to 7, so that is positive. So now when I calculate the entropy of the system, entropy change of the surroundings, remember that equals negative delta H reaction divided by, or actually in this case system, which is my reaction, divided by temperature in Kelvin. So I'm going to do negative times negative 2044 kilojoules divided by my temperature. Now my temperature is 25 degrees Celsius, so I'm going to add 273, and I'll get 298 Kelvin for my temperature. So I'll divide by 298 Kelvin. Now negative of a negative is positive, so my entropy is going to be 6.86 kilojoules per Kelvin. Now, generally, entropy is measured in joules, so you can multiply by 1,000 to get that in joules, but for the purposes of this, we're not calculating the end result, so I'm not too worried. So determine the sign of the entropy change for the universe. So remember, delta S universe equals delta S system plus delta S surroundings. Delta S system, we said, is going to be positive because we have 6 molecules going to 7, so we had an increase. And then delta S surroundings ended up being a positive value. So positive plus positive, so that means my delta S, my universe, is a positive number. And so that means that the reaction, yes, will be spontaneous, as is. And we do know that when we burn propane, that happens on its own. Once we get that going, there's no stopping it. Here's another practice problem where we have nitrogen plus oxygen going to dinitrogen monoxide. It has an enthalpy of reaction of 163.2 kilojoules. So calculate the entropy change of the surroundings if it's happening at 25 degrees Celsius. So delta S surroundings equals negative delta H system or reaction over temperature. So that equals negative times 163.2 kilojoules divided by, again, 298 Kelvin. So that ends up giving me a value of negative 0.5477 kilojoules per Kelvin, or 547.7 joules per Kelvin if I times by 1,000. That's A. B, determine the sign of entropy for the system. So I have 1, 2, 3 molecules going to 2. So it went down. So delta S of my system is negative. So C, sign of entropy change for the universe. So remember delta S universe equals delta S system plus delta S surroundings. So I have a negative value for system plus a negative value for my surroundings. So that's negative. So this is non-spontaneous. Okay, a reaction has a delta H reaction of 107 kilojoules and a delta S reaction of 285 joules per Kelvin. At what temperature is the change in entropy for the reaction equal to the change in entropy of the surroundings? Okay, so that means I want delta H surroundings equal delta S system. Oops. Okay, so delta S surroundings, remember, is negative delta H over T. And delta S system is going to be delta S reaction, right? Because that's the thing we're studying. So delta H of my system, or my reaction, is, let's just put it in joules. So we'll have negative times a negative 1.07 times 10 to the 5th joules over the temperature we're trying to find. That's going to be equal to 285 joules per Kelvin. So what we're going to want to do is find the temperature at which that happens. So I'm going to cross multiply. So I'm going to bring my temperature up here and my entropy down here. So now what I get is positive 1.01 times 10 to the 5th joules over 285 joules per Kelvin. That equals my temperature. Notice my joules are going to cancel. My Kelvin will come up top. And what I get is my temperature is equal to 375 Kelvin. So we're going to do more of that later in a more explicit way. And I think it's kind of fun. So let's talk about how temperature impacts the enthalpy or entropy change of the surroundings. So remember that the change in the universe of entropy is equal to the entropy of change in the system plus the surroundings. So if I have a system that is cold, so I have a low temperature. So in both of these cases, delta S is negative, so not being favorable, right? So if I have a cold situation, so I have my delta S surroundings equals Q over T. So when I'm cold, my temperature is really small. So then when I divide by a really small number, my delta S of the surroundings gets really big. So this is going to be a large positive value. So that means that when I add these two together, I could have a delta S of the universe that's positive, and that's going to be spontaneous. So when heat is added to surroundings that are already cool, there's going to be more of an effect on S than if we have something that is hot. If I have something that has a high temperature, so delta S surroundings equals Q over a high temperature, so now I have a big T. Now I'm dividing by a larger number, so my delta S is going to be a bit smaller. So I'm going to have my delta S surroundings be smaller than it would be under a low temperature situation. So it's going to be, temperature is going to be more important when we have a cool situation, so the entropy of our surroundings. So when we have water freezing, when we're below 0 degrees Celsius or 273 Kelvin, the heat that gets released when we freeze, right? Because if I add heat in, I would melt. So heat, therefore, has to get released when we freeze. So it's an exothermic process. That is going to be, it's cold enough for the delta S of our surroundings to be, to outweigh the delta S of the system. So therefore, my universe is going to be a positive value like it is here when I'm below 0. So water would freeze spontaneously, even though it is I'm decreasing my entropy because I'm going from a liquid to a solid, because the exothermic reaction that is involved is the temperature is low enough to outweigh the condensation or the lowering of randomness. When I have a system that has an entropy change that's unfavorable or negative, the surrounding must be favorable, i.e. positive, for it, and large, right, for it to happen spontaneously. So for our delta S of the universe to be positive. So this all ties together by something called the Gibbs free energy. So when we take our delta S universe equals delta S system plus delta S surroundings. And then remember that delta S surroundings equals the delta or the Q of the system over temperature. And when we're under constant pressure, the Q of the system is equal to the delta H of the system. So let's put that in. Oh, and it should be a negative, right? Because it was negative Q over T, so delta H of the system. So what we do is we're going to multiply the whole thing by negative T to get everything on one line. So I have negative T of the universe equals negative T entropy of the system times negative T, which makes this positive, and that T goes away. So here you see that's how we get this equation here. And what they do is they define a new term, which is the Gibbs free energy, which is the maximum amount of work energy that can be released to the surroundings by the system at a constant temperature and pressure. So we call this the chemical potential. It's kind of like the type of stored potential or energy in a mechanical system. And it involves not only the enthalpy of a reaction, but the entropy at a given temperature as well. So it combines the entropy and enthalpy components. So the end result is delta G, or Gibbs energy, of our system is equal to delta H of our system, we can even put reaction, minus T delta S. Now everything is related to the system, and so that's kind of cool. So because delta G is the same thing as negative T delta S. So remember, when delta S universe is positive, that's when something's spontaneous. Now if I take this positive value and multiply it by a negative T, that means that when delta G, since that's what this whole thing is, when delta G is negative, we have a spontaneous process. Okay, so delta G being negative tells us if a process is going to happen spontaneously. So it's going to consider whether the enthalpy is favorable for a process to happen, and if the entropy is favorable for a process to happen. And so what we get, so we know that when delta H is exothermic, so when delta H is negative, that's a more stable system. We are going from a less stable reactants to more stable. So this is favorable. We also know when delta S of our system is positive, when we're increasing randomness, this is more favorable. So when I plug those in, so if I have, let's go down here, delta G equals delta H minus T delta S. If I have an exothermic process, so delta H is negative, and I subtract a temperature times delta S being positive, then this is a negative minus a positive. So I get a very negative value for delta G. So, and that tells me that that process is going to happen spontaneously. Alternatively, I could have an endothermic process. So that's not very favorable. Minus T times a decrease in entropy. So I'm going to a less random state. So I have a positive minus a negative. So I'm going, that's basically turning into a positive. So I'm getting very positive. So that will be positive all the time. So that's always non-spontaneous. So an endothermic process that decreases in entropy will always be spontaneous. Then we have two other situations. So I have the situation where I have an exothermic process that has a decrease in entropy. So I'm going down in my randomness, getting more ordered. So I have an exothermic that's favorable minus temperature times a more ordered system. So this can be spontaneous only when the entropy component is very, very small. So this is spontaneous when our temperature is low. So basically, if my temperature is really low, then this component is really tiny and my exothermic process is outweighing the more ordered system. And then the last one is if I have an endothermic process, positive enthalpy, minus temperature times an increase in disorder. So this is a more favorable process because it's increasing in disorder, but because it's endothermic, it's not. So the enthalpy part is not helping me be spontaneous, or the entropy part is. So in order to make this process happen, we need to be at a large temperature. So this is spontaneous. Oops. At high temperatures. Okay, so I know this is a lot to wrap your head around, but these are the trends. We're eventually going to calculate numbers and see if we get a negative value for delta G or positive, right? If it's negative, it'll be spontaneous. But just looking at the values, we can kind of predict whether it's going to happen. So here I have nitrogen dioxide, 2 of them, or dinitrogen monoxide, going to 2 nitrogens and 1 oxygen. So I have 2 things going to 3. So I'm getting more, I have a more disordered system. So delta S is positive. This is also an exothermic process. So if I plug those signs into here, I can see that this will always give me a negative delta G, no matter what my temperature. And if I have 3 molecules of oxygen going to 2 molecules of ozone, that is an endothermic process that decreases its disorder. So if I plug those in, it will always be non-spontaneous. Then I have the case where I'm going from a liquid to a solid, so that is a water freezing. So that is an exothermic process we talked about earlier, and it decreases disorder. So that happens, we know, water will freeze when it's really cold. So it's spontaneous at low temperature, but non-spontaneous at high temperature. And lastly, we have a liquid going to a gas, so more disordered system, right? We're going from a liquid to a gas, so I'm getting more random. But it's an endothermic process because I have to add heat to get it to happen. So this process will happen spontaneously only at high temperatures. And it has to do with the trends here. And we know that from our lived experience, but it also depends on the thermodynamics. So, like we were saying, delta G will be negative when enthalpy is negative and entropy is positive. Exothermic and more random. Delta H is negative and really big, and delta S is negative but very small, so that could be low temp. And delta H is positive, but delta S is positive and large, so that would be at a high temp. There we go. So this will be spontaneous, right? Delta G will be positive or non-spontaneous when delta H is negative and delta S is negative and large, or we have high temps. So kind of the opposite. Delta H is positive, so endothermic, and delta S is positive but really small, so it's not contributing enough, which means low temp. Or if delta H is positive and delta S is negative, will always be spontaneous. And when delta G is 0, then our reaction is at equilibrium, which we'll talk about a lot in a future chapter. Okay, so let's consider this reaction. I have carbon tetrachloride going to carbon and 2 chlorine molecules. Notice my delta H is positive. That's an endothermic process. And delta S is also positive. I'm going from 1 to 3 molecules. So that makes sense. So calculate delta G at 25 degrees Celsius and determine if it's spontaneous. So we'll have delta G equals delta H minus T delta S. So we're just going to plug in. Now key thing, notice delta H is in kilojoules and S is in joules. So let's put our S in kilojoules. So we'll divide by 1,000 joules per kilojoule. So that means that my delta S will be positive 0.1422 kilojoules per Kelvin. So I'll have 95.7 kilojoules minus 25 degrees Celsius is 298 Kelvin. That's important. And then times by 0.1422 kilojoules per Kelvin. Okay, and one thing I want you to consider is kind of predicting, is it going to happen or not? Like just from the value. So I have endothermic. Now that's not very favorable. And delta S is increasing. So that is favorable. So this reaction is going to happen when T is big, so we can increase that entropy. So is room temperature high enough? Let's calculate it. Once we put those values in, we get 53.3 kilojoules. Positive. So non-spontaneous because our delta G is positive. So temperature was not high enough to outweigh. We can see the entropy did bring down the enthalpy piece. It went from 95.7 down to 53. So it did bring it down, but not enough. So at what temperature will it become spontaneous? Well, we go from a positive to a negative at the point 0. So we're going to set delta G equal to 0 and then resolve delta H minus T delta S. So we're going to solve for temperature. So I'm going to add T delta S to the other side. So I get delta H equals T delta S. And I'm going to divide by delta S to get rid of that. So temperature equals delta H, which is 95.7 kilojoules, divided by my delta S in kilojoules, 0.1422 kilojoules per Kelvin. And that gives me value. Notice my kilojoules cancel out. My Kelvin will flip up top, and my value is 673 Kelvin. Here is another one. I have a process where ethane is reacting with hydrogen to form ethane, and it's an exothermic process, but notice I have 2 molecules going to 1, so I have a decrease in entropy. So let's calculate delta G. Delta G equals delta H minus T delta S. Now just knowing that we have a negative here and a negative here, so a negative minus a negative. So the enthalpy part is a favorable, but the entropy is not. So in order for this process to happen, the temperature needs to be low. So is it low enough? Let's check. So I'm going to plug in my values. Delta H is negative 137.5 kilojoules minus the temperature, 298 Kelvin. And let's convert this over into kilojoules, joules per kilojoule. So I have negative 0.1205 kilojoules per Kelvin. So negative 0.1205 kilojoules per Kelvin. And that gives me negative 101.6 kilojoules. So this is spontaneous. Yes, it is negative. Does it become more spontaneous or less spontaneous as the temperature increases? Well, if I increase the temperature, I'm going to make this delta S grow. So it's going to become less spontaneous or more positive as we increase the temperature. Okay, so we're getting back into standard conditions. Again, another way that we can kind of unify the conditions for scientists to report their data. So standard state is defined as gas being pure and exactly at 1 atmosphere, solid or liquid being exactly at 1 atmosphere, and temperature usually 25 degrees Celsius. And then solutions being at a concentration of 1 molar. So the third law of thermodynamics says that we have a perfect crystal is going to have an absolute entropy of 0 joules per mole Kelvin when it's at absolute 0, which is at 0 Kelvin. Okay, so that is basically saying that because we haven't actually been able to get at absolute 0, which means that all molecules will have an absolute entropy that is positive. So before we were able to say, delta H of oxygen gas is 0. Now oxygen gas, its enthalpy is still 0, but its entropy is not 0 because it hasn't, it's not at 0, not at 0 Kelvin, and it's not a perfect crystal. Technically, every substance has some kind of or many substances have lots of defects, and so to be a perfect crystal, you have to be perfectly arranged, because you're therefore only going to have one arrangement, one possible macro state that you can have to get there. when we have a reaction, we're going to be able to calculate the entropy of our reaction. When we have a final condition or products that are more random, then our delta S of our system or reaction is positive. This is favorable, as we talked about, helping our process become spontaneous. When our final condition is more ordered than it was at the beginning, and for our reactants, then our delta S is negative. So this entropy change is unfavorable, so it doesn't help our process be spontaneous. So we need a really high exothermic reaction to help it to be that way. So to calculate the delta S of our reaction, we're going to do, same as we did with enthalpy, we're going to take the products minus the reactants, and we'll look up the S of our chemicals of interest or species in a table. Since entropy is an extensive property, it holds the same rules as our enthalpy did. So its state that it's in, whether it's the allotrope or the kind of structure it's in. So, for example, diamond can have multiple different allotropes, whether it's carbon or as graphite or as diamond. How complex the molecule is, how big it is, and how much it's kind of broken apart or dissolved. Gases have higher entropy values, so we can see water vapor has more than double the entropy than it does in the liquid phase, and then solid phase has even lower. So here is a table. There are more, just like the enthalpies. Our table in the back of the book is going to be very, very helpful. Okay, so just kind of comparing these different properties. We have molar mass. So the larger the molar mass, the larger the entropy. That is because we're having more energy states for the electrons to be in, more vibrations for them to be in. With allotropes, it has to do with the structuring. So the less constrained molecules are, or the atoms are in the structure, the larger the entropy. So for example, diamond is much more rigid because they're stuck in 3 dimensions, where for graphite, they're only confined in 2 dimensions. So that makes it less constrained. So graphite's going to have a higher entropy value than diamond would. And then dissolution. So dissolved solids are, for the most part, going to have a higher entropy than when we're in the solid state. And that's just because they have more degrees of freedom. They're able to move around a lot more when they are dissolved. And then the molecular complexities is also important. So molecules that tend to be more complex, so more connections, they have more atoms attached. Even if they have the same molar mass, if they have more atoms within it, now we have more vibrations, rotations, kind of we get this like wagging here. So if I have carbon monoxide versus ethene, even though they have very similar molar masses, when I have 6 atoms versus 2, I have more ways that I can move around. So I'm going to have more entropy. And here I have molar masses of, so argon is technically larger than nitrogen monoxide, but because it has 2 atoms in nitrogen monoxide that are able to vibrate and rotate and bend, they're going to have a higher entropy. So more complex molecules have higher entropy in general because there's just more availability for them to move around. So standard entropy changes for reactions is the change in the absolute entropy of the products minus the reactants under standard conditions. The entropy value for everything is going to be a positive value. So we will always do products minus reactants times their coefficient. So let's do it for this reaction here. I have 4 ammonia plus 5 oxygen going to 4 nitrogen monoxide plus 6 waters. Okay, we can predict. I have 9 gases here and 10 gases here, so I'm increasing. So I can predict it should be a positive value. So I'm going to have delta S of my reaction is going to be the delta S of my product. So 4 times nitrogen monoxide plus 6 times water minus my reactants. So 4 times ammonia plus 5 times oxygen, just like we did with enthalpy. Okay, now we're going to go look in the book for these S values. So the S value for nitrogen monoxide is 210.8 joules per Kelvin, mole Kelvin technically, plus 6 times water. Now it's water vapor, water gas, so we're going to need to make sure we have the right value, which is 188.8 joules per Kelvin. Okay, and then minus our reactants, which is 4 times ammonia, which is 192.8 joules per Kelvin, plus 5 times oxygen, and unfortunately it's not 0, it's 205.2 joules per Kelvin. Okay, so what we get for our reactants, or products, is 1976.0 joules per Kelvin minus our reactants, which is 1797.2 joules per Kelvin. So doing that math, we get delta S of our reaction of positive 178.8 joules per Kelvin. So it is a positive value, just like we predicted based on the molecules and their structures. So good job. Okay, let's do it for this reaction here. I have hydrogen sulfide and oxygen reacting to form water and sulfur dioxide, all in the gas phase. So I have 5 going to 4. So I'm actually decreasing, so I'm going to predict a negative value. Let's see. I have delta S reaction is products minus reactants, so 2 times water plus 2 times sulfur dioxide minus reactants, 2 times hydrogen sulfide plus 3 times oxygen. So let's plug those values in. We're going to look them up in the book. We get 2 times 188.8 joules per Kelvin plus 2 times sulfur dioxide is 248.2 joules per Kelvin minus 2 times sulfur dioxide is 205.8 joules per Kelvin plus 3 times oxygen, which is 205.2 joules per Kelvin. Okay, we get our reactants minus our products, and our end result is negative 153.2 joules per Kelvin. So it is negative. Good prediction. Okay, so we already figured out one way we can calculate delta G, and that is with our equation delta G equals delta H minus T delta S. But there have been other ways that chemists have been able to figure out. Since reactions involve enthalpies, or Gibbs energies, free energies, we can calculate the free energies. There's actually tables for free energies of formation for different species. So just like before, we could do products minus reactants, and so we will. So we could either do that when we're at not at 25 degrees Celsius. We could also do our Hess's law-esque formula, or we can solve products minus reactants if we're at standard conditions. So here we have one possible step in a formation of acid rain is sulfur dioxide reacting with oxygen to get sulfur trioxide by that reaction, and our delta, we want to find delta G not at 25 degrees Celsius to figure out if it's going to be spontaneous or not. So the fun part is we get to do, since we're not necessarily at standard conditions, what we get to do is find delta H of the reaction, find delta S of the reaction, and then plug it in. Fun. So let's do that. Delta H, we're going to do products minus reactants. So I'll do, for this reaction's products, so 1 times SO3 minus reactants, SO2 plus 1/2 of oxygen. And I'm actually going to copy that, whoops, and put it down here for later for delta S, because we're going to need to do the exact same calculation but just with different numbers. So for delta H, we have sulfur trioxide is negative 395.7 kilojoules per mole, minus sulfur dioxide is negative 296.8 kilojoules per mole, plus 0, because oxygen is 0. So our delta H of our reaction equals negative 98.9 kilojoules. So now for delta S, for reaction, we're going to do the same thing, but for our entropies. So our entropy of sulfur trioxide is 256.8 joules per Kelvin, minus sulfur dioxide, 248.2 joules per Kelvin. Now we will add the oxygen plus 1/2 oxygen, which is 205.2 joules per Kelvin. So when we plug all of that in, we get negative 94.0 joules per Kelvin. So we will now plug into our delta G equation. Delta G equals, our reaction, delta H minus T delta S. So we want to make sure our energy units are the same. So I'm going to actually divide this by 1,000. And joules per kilojoule, and that will give me 0.094 kilojoules per Kelvin. So I'll plug that in. I get negative 98.9 kilojoules for the entropy from right here, minus temperature. Now I'm at 25 degrees Celsius, so it's 298 Kelvin, times by my entropy, which is negative 0.094 kilojoules per Kelvin. So my delta G ends up being negative 70.9 kilojoules. So yes, spontaneous, because it is a negative value. Cool. Let's do it again. So I have nitrogen monoxide plus 1/2 oxygen going to nitrogen dioxide. If we look up in the table, there's lots of values, so you'd want to go find those. I'm going to encourage you to pause. If you haven't been pausing at the beginning of every problem, you should be, because you should try it out first. So go look in your appendix C or whatever appendix it is to find the table with all of the thermo values in it. Okay, assuming you did, let's now do it. So let's do delta H of our reaction equals our products minus our reactants. So NO2 minus, that's our product, minus reactants, NO plus 1/2 O2. Again, I'm going to copy it because we're going to do it for entropy as well. So for nitrogen dioxide enthalpy, I have 33.2 kilojoules, minus nitrogen monoxide is 91.3 kilojoules, plus 0. So my enthalpy ends up being negative 58.1 kilojoules. Awesome. Now for enthalpy, or entropy, delta S reaction, same thing but entropy values. So I'm going to have nitrogen dioxide is 240.1 joules per Kelvin, minus nitrogen monoxide 210.8 joules per Kelvin, plus 1/2 times oxygen, which is 205.2 joules per Kelvin. So that ends up giving me a value for delta S being negative 73.3 joules per Kelvin, and I'm just going to immediately go to kilojoules. So divide by 1,000 joules per kilojoule. So I end up getting negative 0.0733 kilojoules per Kelvin. So now delta G is delta H minus T delta S. Such a fun process, right? So many steps. So delta H is negative 58.1 kilojoules. And we're going to subtract temperature, which is at 25 Celsius, so 298 Kelvin, times negative 0.0733 kilojoules per Kelvin. And my delta G ends up being negative 36.3 kilojoules. So, yes, this one is spontaneous also. So in this problem, it basically wants to say, we're going to go back a couple slides and figure out, is the reaction more or less spontaneous than it was before? So remember, before we had a value at 25 degrees Celsius, our delta G reaction was negative 70.9 kilojoules. Okay, so is it more negative, so more spontaneous, or is it more positive, getting closer to zero at 125? So we're going to plug in again. We don't have to recalculate. We already did delta H and delta S. So do delta G equals delta H minus T delta S. Now our temperature is different. So we'll plug in our values. Delta H was negative 98.9 kilojoules minus temperature. Now it's at 125. So now our temperature is 398, not 298 Kelvin. And then we'll multiply by our entropy, which was negative 0.094 kilojoules per Kelvin. So our delta G ends up being negative 61.5 kilojoules. So if we compare it to what it was at 25 Celsius, it got closer to zero. It got less spontaneous. So it got more positive than it was before, which makes sense because as we increase the temperature, our negative entropy is starting to dominate. Not quite dominating yet. We can find that temperature, but we're not going to, it's not there yet. So now let's do the exact same thing, exact same reaction, but we're going to do it for a lower temperature, so at negative 55 degrees Celsius. So our delta G, so remember at 25, it was negative 70.9. So now we'll do delta G equals delta H minus T delta S. Now our T is lower, so we'll add 273 to negative 55. So our delta H is still negative 98.9 kilojoules minus temperature now. So negative 55 plus 273 is 218 Kelvin times our entropy still is negative 0.094 kilojoules per Kelvin. So when we plug that in, we get negative 78.4 kilojoules, which makes sense, right? It's more negative, so more spontaneous than it was before, which makes sense because now we're shrinking our unfavorable entropy component and helping it to be the enthalpy to kind of outweigh it even more. A little bit nicer type of process is the free energy of formation of an element or a compound from its constituent elements and standard states, just like enthalpy of formations. And we can find it gives energy of reaction when we do the formations of the products minus the reactants. Keeping in mind, now this one's nice because the energy of the pure elements in their standard states is 0, just like it was before. So that's nice. So these are all measurements. Again, another column in the back of the book, in your appendix. So be checking that out. So we're going to do now products minus reactants. And here's all those Gibbs energies for these components. So this is yet another way to find delta G, and a little bit more straightforward because you don't have to do delta H and delta S. So using the free energies of formation, find delta G reaction. So we'll do products minus reactants. So we'll do CO2 plus 2 times water plus 4 times ozone minus our reactants, which are methane, and 8 oxygens. So right away, oxygen, that's going to be 0. Yay, not an entropy. So we'll do CO2, which is negative 394.4 kilojoules plus 2 waters, water being negative 228.6 kilojoules, plus 4 ozone, which is 163.2 kilojoules. That whole thing minus methane being negative 50.5 kilojoules. Okay, so we just plug it in. Reactant or products being negative 198.8 kilojoules minus this negative, so minus negative 50.5 kilojoules. So our delta G reaction equals negative 148.3 kilojoules. So could you have done the other practice problems like this? Yes, you could. If they're at standard state, they should be, you could have done this, but if they don't give you the delta G's and you're given delta H and delta S, then that's how you would solve it. Here's another reaction happening in your catalytic converter, converting carbon monoxide and nitrogen monoxide to carbon dioxide and nitrogen gas. These are both not good for you. So find the free energy of reaction from the formations. So again, you look in the back of the book for these values. We'll do delta G reaction equals products minus reactants. So 2 times CO2 plus N2, nitrogen, minus reactants, 2 times carbon monoxide plus 2 times nitrogen monoxide. So plug in values. We have carbon dioxide being negative 2 times negative 394.4 kilojoules plus nitrogen. Now nitrogen's in its standard state, so it's 0, minus 2 times carbon monoxide. Carbon monoxide is negative 137.2 kilojoules plus 2 times nitrogen monoxide, and that is positive 87.6 kilojoules. So when we plug all of that in, we end up getting negative, so reactants being negative 788.8 kilojoules minus our products being that, reactants being, so minus a negative 99.2 kilojoules. So we end up getting our delta G being negative 698.6 kilojoules. And that is good. That's very spontaneous. So luckily for us, this process is very much spontaneous, getting rid of those pollutants. Okay, delta G reaction. So basically this is saying that we can use delta G just like we did delta H with Hess's law. So it is a state function. It only depends on the final and initial values. So we can, if we have multiple steps, we can sum the delta G's from the various reactions to get the total reaction. If we reverse it, we're going to flip the sign. So we're going to reverse this value. So if it was positive, it would be negative if we flip the reaction. And if we multiply the reaction by a factor, so if we multiply the reaction by a factor, we'll multiply the Gibbs energy by that same factor. So if I multiply the reaction by 2, I'll multiply the Gibbs energy by 2. So here we go. We have carbon plus hydrogen going to propane. Pretty sure we did this exact same example with enthalpy. So, but now the only difference is the Gibbs of the reaction. So, and these, like for this formation of CO2, that is the delta G formation for that reaction. So we're going to start with carbon. Where do we see carbon? I see it in the second reaction. So I'm going to need to multiply the second reaction by 3 to get it to be the same. So I'm going to do 3 carbons plus 3 oxygens going to 3 carbon dioxides. So I'm going to take that delta G of the second reaction and multiply it by 3. So 3 times negative 394.4 kilojoules. Okay, now that one is done. Okay, hydrogen. Where do I see hydrogen? I see hydrogen here. It's a reactant, but it's not times 4, it's times 2. So I'm going to multiply this whole thing by 2. I'm going to have 4 hydrogens plus 2 oxygens goes to 4 waters. So now I'm going to take delta G of that reaction and multiply by 2. So 2 times negative 457.1 kilojoules. So now that one is done. And now we have that matching up. Now propane. Propane's a reactant here. We need it to be a product. So we're going to flip that whole thing and get 3 CO2 plus 4 water goes to propane plus 5 oxygens. So I'm going to need to take my delta G for that reaction and change the sign. So it'll be a positive 2074 kilojoules. Okay, so notice my 5 oxygens, going to cancel out those 5 oxygens. My 4 waters, cancel out my 4 waters. My 3 CO2s, cancel out my 3 CO2s. So I'm left with 3 carbons, 4 hydrogens on my reactants, and 1 propane. So then I'm going to add all of these Gibbs energies together to get my reaction, my total reaction that I'm interested in. And I end up getting something very similar to close to 0 actually. So it's actually negative 23 kilojoules. So pretty small, but still spontaneous. So that would just happen on its own. Here's another one. We have nitrogen dioxide plus dinitrogen oxide plus nitrogen dioxide going to 3 nitrogen monoxide. So let's approach this friend here. Okay, dinitrogen monoxide. Where do we see that? Okay, I see it in the third reaction. It is, I only want 1, and here it has 2. So I'm going to multiply the whole thing by a half. So I'm going to get dinitrogen monoxide goes to nitrogen plus a half oxygen. And I'll get delta G equals 1/2 times negative 207.4 kilojoules. So that one is done. Now nitrogen dioxide is right here. So it is a product and it's multiplied by 2. So I'm going to need to flip it and multiply it by a half. So let's flip it. 2 NO2 goes to 2 NO plus O2. And then I'm gonna, so delta G equals positive 71.2 kilojoules. And then I'm gonna multiply it by a half. So let's get rid of that and that. So we just need one of those. And then I want a half oxygen. Perfect. So now this top one is done. Now this bottom one. I want 3 nitrogen monoxides, and I already have 1 here, and here, this reaction provides 2, so I'm just going to write it as is. So I have a nitrogen plus an oxygen goes to 2 nitrogen monoxides, and I'll leave it alone, positive 175.2 kilojoules. So to do some canceling, so I have a 1 oxygen here, 1 oxygen here, so those are canceled out. I have 3 nitrogen monoxides, so that's good. I have 1 nitrogen here, 1 here, so those cancel. And then I have N2O and NO2, which is the reaction I want. So I can add all of those up, and I end up getting 107.1 kilojoules. So this is a non-spontaneous reaction. It didn't ask, but might as well talk about it. Okay, so what is so free about free energy? Well, free energy is the maximum amount of energy available that gets released from a system, and then it can do work on the surroundings. So for many exothermic reactions, some of the heat that gets released from our enthalpy reaction, right? If it's exothermic, then there was some energy that got lost. So that ends up going into increasing the entropy of the surroundings. So when that happens, that energy that goes into increasing the entropy of the surrounding, that's not available to do work. So basically it's taking out, the free energy is taking out the amount of entropy that got transferred into the surroundings to increase it. And then some of the free energy is also lost. So basically that energy is lost into heating up the surroundings. So if I have the enthalpy of reaction of this process is negative 76.4, that's exothermic. I also have the entropy of that process is 80.8 joules per Kelvin. That's unfavorable. So the entropy is not helping it. And when I multiply, or add those two together, multiply the entropy by temperature, the Gibbs free energy is negative 50.5. So this is a spontaneous process. So basically what ends up happening is some of the energy, the exothermic process, goes from the reaction and gets transferred into the entropy of the system, leaving only 50.5 to do work, because 24.1 of the heat got lost to the surroundings in the form of entropy. Remember, delta S surroundings equals Q of the system, so heat that came from the system over the temperature. So because our entropy is less than the enthalpy value, then that means that we took some of the heat from that process and used it to increase the entropy of the surroundings. But there was still enough left over to make that process spontaneous. So it's basically a theoretical limit of how much work can be done. If the reaction achieves the limit, then it is reversible. This here is an example of a reversible process, right? It's happening spontaneously. You're basically getting rid of like 1 grain of sand at a time, such that the pressure of the gas inside matches the weight of the sand. So if you just move a little bit at a time, the gas will slowly expand. But then if you add a little bit more, it'll go backwards. So that we can go back and forth because it is a reversible process, and you wouldn't have to add any work to it. In real reactions, right, a lot of these are standard. So most reactions, that free energy is lost as heat, so we do get quite a bit. So most real reactions are irreversible because you're not getting all of the free energy to do the work. We're actually going to lose even more as heat than we would think. So here we have a reaction or a process where our battery is powering our motor to do some work. So electrical current is flowing, and if you've ever felt the wires or around the system, you feel quite a bit of heat getting emitted, and so it's not a perfect system, so it's not going to be a reversible process. So that ends thermodynamics, but we are going to see it quite a bit throughout the rest of the semester because it's very, very important in chemical reactions.